Okay, so what we were doing last time, we were like looking at one-dimensional system. Okay, so we were looking at a very simple but important system, which was a finite potential well. So we had some potential energy V of x, and it was a potential well whose depth was V0. V0 is a positive number. So so this is minus V0, and the width of the potential was A. This is x, this is 0. Okay, and we're looking at energy, bound state energy. So we are looking at energies which were the total energy was negative. Okay, so the bound states, and so we, so we could have said that this is region 1. Say this is region 2. This is region 3. And then the solution is psi is going to be e to the power I, e to the power k1 of x in region 1, where k1 is essentially this one. So yeah, k1 is 2m b naught minus e divided by h bar square root, right? So this is, and in the previous class, we wrote down what the boundary conditions are, and we found 4 boundary conditions. And because we are free to fix the normalization of the overall normalization of our wave function, that we took advantage of that to fix this coefficient to be 1. So if you do this, then the other coefficients turn out to be, so in region 2, it's 1 over alpha sine of k, and this is quite easy to derive, k minus a by 2 plus n pi over 2. Okay, this is when in region 2. And then in region 3, we have minus 1 n plus 1. N is a positive integer. It's a 1, 2, 3, dot, dot. So its parity will depend on, the sign will depend on the value of n. So this is minus k1 x minus a. This is in region 3. Okay, and we saw that to solve for the energy, we need to have a what kind of equation did we need to solve?
Wasn't it that transcendental equation?
Yes, transcendental equation, a very religious equation, right? So, so gamma alpha equals to n minus 1 pi plus 2 cosine inverse of alpha, where n goes from 1 to 3 dot. It's an integer. Okay, and the way we solved it, just kind of review this because this is not easy. so it doesn't hurt to review these things. So what we do is that we take the left-hand side, and in the left-hand side, the first thing we do is that we said, okay, let's set n equals to 1. Then this first guy is not there. And alpha, let me remind you what alpha was. Alpha is given by Ka by gamma, where gamma is the depth of the potential, square root of the depth of the potential. So it's 2m v0 a squared divided by h bar squared. Okay, so alpha measures the energy. Okay, so alpha, but alpha on, so this is alpha, and alpha goes up to 1, and so in the first one, when alpha is 0, we see that this thing is going to be the way this is designed is that this is going to be pi by 2, right? Because we know that cosine inverse of 0 is pi by 2. So that means that this term is going to be pi. And this, of course, this guy is not there for n equals to 0. So, so what we will see is that we will see if this is a pi, as alpha increases, it reduces from pi down to 0. So this is a 1, where alpha becomes 1. Okay, and similarly, for n equals to 2, we just get a shift. This thing is no longer 0. We just get the same graph being translated in the vertical direction. Okay, so maybe what we can do is that we can just copy this. Okay, I have to copy multiple parts of it. Okay, so, and then okay, so on and so forth. So this is the right-hand side of the equation. Now, the left-hand side of the equation will depend on gamma. It'll basically be, if gamma is large, then that means that the potential is deep. So the left-hand side of the equation is straight line, in terms of alpha, but it'll depend on, its slope will depend on the depth of the potential. So for very low depth, the potential is like this. So this is gamma equals to 1, and then gamma equals to 2, or no, this is gamma equals to 4, and then gamma equals to, yeah, if you increase gamma, it just goes like this, okay? And if gamma is infinite, which is the infinite potential, well, you can see that this line will essentially, go towards the, this will go towards the vertical axis. And in that case, there are an infinite number of intersections between the straight line and the red line and the green line. And for a given value of gamma, these are the energy, the possible energies are the intersections, okay? So here we've got 1, here we have 2, here we can see 3, and there's perhaps going to be more because we haven't specified the values. Okay, so these are the, now if I look at this formula, And I say, okay, if I put gamma alpha equals to 1 so that I'm looking at this extreme edge, then I get that, this becomes 1. This is n minus 1 pi. And, this is going to be 0, right? So basically, if I solve that equation for n, I get a value of n, okay? And it's not going to be an integer in general, but the integer part of that n is the number of intersections that we are going to get between the straight line and these curved lines. So given a value of gamma, the integer part of, so what I want to say is that given a value of gamma, the integer part of gamma over pi plus 1 is the number of energy eigenvalues, okay? All right. Another thing you can verify is the following, is that, if you look at the wave function in the region 2, in region 2, the wave function is, it's 1 over alpha sine of kx minus a over 2. And this is best done for picking specific values of n and trying it out. That this thing, the wave function psi, will have n minus 1 zeros for finite n. In other words, suppose that if I take n equals to, say, n equals to 5, then if I plot the wave function in the background of where 0 is, where 1a is, so this is where the potential is, then the wave function will look something like this. Let me use a different color. So this is 1, this is 2, this is 3, and I ran out of space. Okay, let's do it again. This is 1, 2, 3. Let's do this. 4, and yeah. Okay, so this will have, for n5, there will be 4 places in which the finite part of x, in which 1, 2, 3, 4, where the wave function will intersect the x-axis. So this is actually a generic feature. So this is a generic feature of one-dimensional bound potential, okay, or bound states. And perhaps we'll prove this as a theorem in the next class, okay. So So what does that tell us for the ground state, which is going to be n equals to 1? For the ground state, there will be no intersections with x equals to 0 and the finite part, right? Okay, so which is something that agrees with our intuition that we developed in conjunction with, say, the infinite potential well, because inside this region there is no potential energy, or the potential energy is So in that region we expect the same solution as the infinite potential well, but here we expect it to be decaying, right? Okay, so this is the ground state psi1, also known as psi0. Okay, so this is basically what I wanted to say about the finite potential well. Are there any questions?